Good morning, my friends. Welcome to our discussion on error. We're going to follow up from yesterday. Sorry I'm not with you again today. I will definitely be back tomorrow, so I'll see you guys on Friday. Today we're going to talk about how we report error and then what we can do to reduce our error when we're using stopwatches in particular, and more generally whenever we're taking data. So to do this, what I want you to do is open up your lab notebooks to the lab we were just on, the stopwatch, the reaction time lab, and let's get rolling. So at this point, everybody should have their lab notebooks open, ready to go. If not, let's pause the video, let people catch up real quick. Otherwise, I'm going to get going. So as we report error, we really have two things to think about. One is the amount of error, like one of those columns is amount of error, and the other is the percent error, and that's that second column. And so to start the discussion, let's talk about this. So let's say you were measuring the distance of something and you're only off by half a centimeter, 0.5 centimeter. That's like this much, right? So it's like this. Well, it's probably big on the screen because my hand is close to the video, but it's like not very much, like this little bitty bit, right? And the question is, well, is that a lot of error? Or is that a small amount of error? Is it good or bad amount of error? So take a minute or two now with your group of four at your table, and I want you to discuss that question. Is 0.5 centimeters of error a good thing or a bad thing? Is it a lot of error or a small amount of error? All right, pause the video and let's do that now. All right, so you guys have all had a chance to discuss that. And I'm hoping that you came to the realization that this much error, 0.5 centimeters, could be a big deal or it could be no big deal depending on what you're measuring. The key here is, what are you measuring? Now, if you're measuring something really small, like a little ant on the ground, that's like this long, and being off by this much, it's like, well, that's ridiculous. That's way off. Whereas if you're measuring the height of a building instead, it's like being off by this much for the height of an entire building. Well, that's fantastic measurement. So your amount of error really doesn't tell you how good your data is. It's when you compare your amount of error to the thing you're measuring, it tells you it. And that number is our percent. Here's a graphic to help you. Let's say these two blocks represent the amount of error. We could be off by that much of the block when we measure the distance of something. And in this first one, we're going to measure something that long. So we're measuring something like this, and we could be off by almost half of it, right? That's like 50% error. That's a huge deal. It's like you could be halfway wrong. Now in this next one, it's the same amount of error. So you can see here that this block is the same size. This error block is the same size, the same amount of error. But watch what happens when I compare it against, well, if I'm measuring something really long and I'm off by this amount, well, that's not that big of a deal anymore. It's like, okay, that's reasonable. I won't be off by that much. But if I'm measuring this, it's like, wow, that's off by, it's like 50% of its error. And that's a big deal. So as we move forward, the best thing to report is going to be percent error and not absolute error. Now this slide, I want you to write this down in your lab notebook. So open up to a blank page and write this slide down in your lab notebook. When reporting error, it's better to report the percent error. That way we actually know how good your measurement is. Instead of just saying, oh, I was off by like half a centimeter, say, oh, I was off by 2% or 3%. And we need to get our, I should say our there. We need to get our percent error into the range. So this should be an R there. I apologize for that. Our percent error into under 5% whenever possible. So if you've got over 5% error, it's going to be really hard to see patterns. So we want to try to reduce to under 5%. That's our threshold. So I'm going to get this down in your lab notebook. And then I'm going to write down two equations real quick. You have them already, but then I'm going to write them down again. Amount of error. The equation for this is equal to let's see, your time, whoops, minus the correct time, the actual time. And here, if you were measuring distance, this obviously would be your distance minus the actual distance. And I'm going to put this straight line bracket around it. Maybe you've had this in math class before. This straight line bracket refers to absolute value. So what this means is we don't care if it's positive or negative. Everything just becomes positive. We just kind of ignore the negative sign. All we care about is how far off you are, not whether you're high or low. And the other one I'm going to write down, I want you to write these two equations down as well, is the percent error. And the percent error is going to be the amount of error. So whatever number you get from up there, divided by the actual time. And again, if you were measuring distances instead of time, it would be the actual distance. And that would give you your percent error. So this compares your amount of error to how big it is. Right? All right, so those are two equations. Hit pause if you need more time to write this down. If not, we'll move on to the next slide. So let's read over this. So we have David measured the time it takes for a ball to fall from a second-story bedroom. And he measured that time to be 0.5 seconds. Whoops. But David knows from just using a stopwatch that he might even have 0.2 seconds of error in that number. Right? Which is a really short amount of time, right? He's pretty quick. His thumb's good. And then Jessica measures how long she's been alive. And she figures out she's been alive for this many seconds. The only problem is she doesn't know what time she was born on her birthday. So she could be off by an entire day worth of time, which is 86,000 seconds. So this number could be high or low by 86,400 seconds. She doesn't know. So the question we're going to ask here is three questions, really. Which person has the smallest amount of error? Which one has the smallest percent error? And which one has the best measurement? So that's interesting. So this is a judgment here. So those three things I want your group to work on. I want you to work on calculating the amount of error each of these people have, David and Jessica. Again, here's David, here's Jessica. Their amounts of error as well as the percent error and which one has the best measurement. I want actual numbers for this. I want a number for this. And then this is going to be a value judgment of which one do you think does the best job of measuring time. All right, take time now. Hit pause and get that done. When you're ready, let's go. We'll play again. All right, so we all got it. Hopefully we saw that the percent error here is the 0.2 divided by 0.75. And that should be times 100. I should have put that in the last slide. My apologies. So 0.2 divided by 0.75 is equal to 27% error. So about 27% error for David. And that's about 0.2 seconds of error, right? So there's his amount error. There's the percent error. And for Jessica, her amount of error is huge. It's 86,400 seconds. But the percent error, I find that by taking the 86,400 and I divide it by 482,500,832 seconds. And we find that that is, ready for it? 0.018% error. So even though the amount of error here is way larger, that time she's measuring is so much bigger, her percent error is super tiny. Super tiny. Super big percent error. So here's the way we reduce error when we're doing with measurement with times or any other measurement, in fact. We try to measure the biggest measurement we can. We extend that time measurement. So you saw in your lab yesterday when it was half a sec or 1.5 seconds, huge percent errors. 5 seconds, smaller percent error. 20 seconds, even smaller percent error. And remember, we're trying to get under that 5% range. So when using a stopwatch, the best thing to do is time the longest time you possibly can. And that's true for all kinds of measurements. So you always want to measure the longest thing you possibly can so you reduce your percent error. All right, awesome. That does it for our error conversation. Next, we're going to be talking about Pendulum Labs. And what we're going to talk about here is a pendulum is a heavy weight hanging from a string that swings back and forth. You may have seen it before, like a wrecking ball swings and bashes into a building and knocks it down. A wrecking ball is an example of a pendulum. And somebody's swinging on a swing set. is an example of a pendulum. It swings back and forth and back and forth. And that back and forth motion is called, in physics, we call that an oscillation. An oscillation, which is that back and forth motion. Now, a few definitions here. A cycle. This word right here, a cycle means one full swing. So it's a there and a back. Not just a there, but a there and a back. That's one cycle. Okay? Some people want to call it that as two because it's like over is one, back is two. That's not right. All the way there, all the way back is one cycle. Now, the time it takes to complete that cycle has a very specific name, and that's called a period. So the period of the pendulum is the time it takes to swing there and back. So if we're looking on a pendulum, we have a heavy thing hanging from a string. It's going to swing to this place in the future, over on this side, and back. So there and back, that's a cycle. And the time it takes is the period. I'm going to pause there and let you guys catch up. Go ahead and pause the video, and when you're ready to go, hit start again. Get this picture drawn as well. All right, so we got that down. What I want you to consider next is what variables, whoops, I misspelled variables. That should be a V. Variables affect the period. So at this point, there's a document. Sorry, the handwriting's getting terrible. There's a document on my main table there, the demonstration table, top right-hand corner. I'm pretty sure I left right there in the corner. That's for the Pendulum Labs. And if you can hand out one of those to everybody gets one of those, that'd be fantastic. Take the time to read that introductory sentence there. And then in the space, right in the middle of the page, in the space, as a group, you're going to try and answer this question. You're going to try and figure out what are all the variables that might affect the time it takes, the period, the time it takes to go from here to here. So go ahead and pause the video and do that. All right, so we've got this whole list of variables ready to go. Now the three that we're going to start off by testing, and I'm sorry I'm not there to help you with figuring all this stuff out, but the three we're going to start testing are these. So weight of the pendulum, that was one of the ones hopefully that we found out, that we thought might affect it. The angle we release at, and here's what that means. So if we go here, like the pendulum is normally right down here, hanging here still, the release angle is this angle here. It's how high you draw it up this way. So that's the release angle. And then also we're going to test the length of the pendulum. Now when I'm back Friday talking to you guys, if you have some other ones that you really want to try and test out, we'll totally talk about that at that time, and I'll run you through and say okay or no on those guys. All right. So each group is going to choose one of these variables to test first. Over the course of the next 4 days, you're going to be testing all three of the variables, but we got to design our labs first. And remember, lab starts with title. So in your lab notebook, you're going to write this stuff down. Title of the lab. You're going to do a question you're trying to answer. Question. You're going to do a hypothesis. You're going to do a table of variables. So remember, your variable table looks like this, like that, like this. Here, manipulated variables, responding variable, and then control variables. You're going to list your control variables here, right? So that's where that goes. And then once you get that done, you're going to work on designing a procedure. So this needs to in sentences and steps. So like step 1, blah, 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 blah. You need to set up, what you're going to do is describe how you're going to make your first measurement of the period of the pendulum. And then what you're going to change each time as well. Make sure you get all in there. It should take I know 4, 5, 6 good steps to really get a good procedure down. And I'll check with these with you guys on Friday. After that, you're going to do one last thing, and that's data table. And up to that point, then you're good for Friday. We're going to start actually collecting data on Friday, not today. And this should be a E, looks like a Z. So if you can get to the point where you have a title, question, hypothesis, procedure written out, variable table, and a data table ready to go for your lab, man, that's going to be fantastic. And then we'll finish this workout, or we'll start collecting data on Friday. And I'll run you through the rest of what we're doing. Now, if you have trouble following that, what I want you to do is look at that Pendulum Lab sheet that you just got. And the pre-lab, the procedure there, will walk you through all the steps of what you need to do. All right, my friends. Work hard, do a good job, and I will see you on Friday.